Okay, hello. Uh, in the last few classes, we more or less completed the design of probability theory as a tool for reasoning. And one of the crucial things that uh, we implemented in this design was the desirable feature of the framework for reasoning, probability theory, being of universal validity. So then the question uh, becomes, for a physicist, the question becomes, how about quantum probabilities? Are they something different from the standard probabilities that we have just seen? So the existence of quantum probabilities really casts doubt on the utility of the whole idea behind a universal framework for inference. So today I'm going to start the lecture by tackling the problem of quantum probabilities. I want to show that quantum probabilities are not necessary, or at least that quantum probabilities are not in disagreement with quantum mechanics. How do you actually derive quantum mechanics? That's going to be another problem that we're going to tackle later. But today, what I want to do is just show that, in principle, there is no problem. The example that I want to do is also pedagogically interesting because it's a good exercise on the use of the sum and the product rules, and also it is a good warning exercise on the fact that all probabilities tend to be conditional on something. So writing down what that something is explicitly is sometimes a very good exercise, because if we forget what it is you're conditioning on, you definitely are going to make mistakes. So let us get started. What I want to do is call my screen, and here we go. The example that I want to tackle is the example of the double slit experiment. Proposed originally by Thomas Young in 1807. What this guy wanted to discuss was the diffraction of light in a screen with two slits, and he wanted to discuss it by drawing on the possible analogy to having waves on the surface of water and putting barriers and seeing the interference effects there. It's sort of amusing that the experiment is nicely described in Young's book, but it's not clear he actually did it. So in a sense, it's a little bit like Galileo's experiment from the Leaning Tower of Pisa, dropping stuff, which is also not obvious whether he actually did it or he just put it in his book for as an illustration. In any case, the experiment has been done with waves, it has been done with light, and even it has been done with quantum mechanical particles such as electrons. If you want to look at it a little bit more, at some point, I strongly advise you to take a look at Feynman Lectures on Physics, Volume 3. And the reason I say this is because there you'll find statements to the effect that, yeah, quantum mechanics really violates the rules of probability, which is exactly what we want to say, what we want to argue now, that no, they don't. The fact that quantum mechanics does not violate the rules of standard probability theory was already noticed in 1957 by a fellow of the name Koopman. I give the reference in my book. But it's one of those papers that's written, published, and ignored. In any case, here we go. So the problem of the double slit experiment is with one in which you have a source from which particles are emitted. Then you have a screen with two slits. And then you have a set of detectors. It may be, for example, a film, so that if a particle hits the film, it leaves a black dot somewhere there. So there is a detection, possibly at some point, D. And the particle is supposed to somehow make its way by going from there to there and maybe there to there. And this is by definition what a screen does, namely it only allows the particle to go through, or whatever it is that's going uh, through the holes. Very good. So let us first look at how we analyze this problem with quantum mechanics. And I want to start by saying there is absolutely nothing wrong with it. Okay. So in quantum mechanics, the quantum mechanical approach to this is that if you want to compute the probability of a detection at D, what you do is you construct a complex number, psi, and you take the magnitude squared, and this is going to be proportional to the detection at D. And this complex number here, let's write it as the complex number that corresponds to the two slits being open. Quantum mechanics says that this complex number is going to be the sum of two alternatives, the quantum mechanical amplitude to go through A plus the quantum mechanical amplitude to go through B. And the way we just take the probability and square it, take the magnitude, take the amplitude psi AB when both slits are open, square it, you're going to get the square of the first plus the square of the second plus additional terms like this. And the idea here is that psi AB magnitude squared is proportional to the probability of detection when both A and B are open. And it's also true that the magnitude square of psi A is proportional to the probability when A is open and when only A is open and B is closed. And similarly, this is the probability when B is open and A is closed. So when we put these things together here, what we have is that, therefore, the probability, I'm using capitals, so let's write it as the probability of detection when A and B are open is not the same as the probability of detection when only A is open plus the probability of detection when only B is open. This is what quantum mechanics says. This is correct. No problem here. But then people add words to this. And that's when the trouble starts. The words that people might add are things like this. The probability that the particle goes through A and, or B is not the same as the probability that the particle goes through A plus the probability that the particle goes through B. And so this is the kind of thing that gives rise to the mistaken idea that quantum mechanical probabilities or that quantum phenomena do not obey the rules of classical probability. Please notice that that is not what I said out here. It just, and we're going to analyze this in a little bit more detail. So to analyze this in more detail, by the way, and the fact that this additional sentence here leads you to believe that quantum mechanics does not obey regular probability theory. This is what leads to all sorts of very, very strange interpretations for quantum mechanics, such as, for example, the Copenhagen interpretation that says that the particles do not have definite positions. It does not make sense to say that the particle goes through one or through another slit or through both. It doesn't make sense because quantum mechanics only refers about the detection, not about what's going on while you are not looking. So all of these additional pieces of language that we add to the mathematical formalism of quantum mechanics are what is precisely being affected by having inadequate notions of what probabilities are. So in order to clean the subject up, let me just put a warning here. This is wrong. But in order to be clearer about what's actually going on, we're going to invent or write down everything that's going on very explicitly. So when you have we need a proposition S that says the particle is generated at the source S. Then we're going to have another proposition. A is the proposition that slit A is open. Well, clearly this is the proposition that slit A is closed. And similarly, we're going to need another proposition B for slit B is open, and the proposition not B, which says that slit B is closed. Very good. What else? We're going to adopt up here another proposition here that says particle goes through A, B, beta, particle goes through B, and finally D, the particle is detected at D. Now, so here we have the several propositions being written out a little bit more explicitly, but it is important, just as we start by making all our propositions have a notation that really cleans up all our propositions, it is very important to start thinking seriously about, if you want to apply probabilities, you have to be very clear about the probabilities of what? So we're definitely going to be talking about the probability of D, detection. But before we start, it is important also to make clear what the model we adopt for these quantum mechanical particles is going to be. So the model is going to be, and this is not about, this is a matter of hypothesis. Whether the model works in real life or not, that's another issue. But we're going to make the model explicit and then just apply rules of probability. The model says that particles have a particle has a definite position at all times. Please notice that this is not the Copenhagen interpretation. In the Copenhagen interpretation, we abstain from saying what the particle is doing or what's actually going on until you have a detection. Once you have a measurement, then you say, okay, now the particle has a momentum, it has an energy, it has a position, it has whatever it has. But it's only after a detection. Before that, you just don't say anything. You abstain from making any assertions. So within the Copenhagen interpretation, particles do not have definite positions. Furthermore, this is the first assumption we're going to make. The second assumption is that as the particle goes from S to D, it's going to follow a continuous path. The particles have definite positions at all times, and these positions change continuously. The particle follows a continuous trajectory. It doesn't jump. Very good. So this is the start. Now we just keep going. What we are interested in is, let me draw the diagram yet again. S, D, A, B, alpha, beta. Very good. Trajectories are supposed to be continuous, so there is no jumps there. Very good. So what we want is the probability of having a detection given that the particle was generated at S and both slits A and B are open. So we're going to start by writing the following assertion, or so the following probability. Start from, here is the probability that the particle goes through slit A or slit follows path alpha or follows path beta through going through A or B, and there is a detection, and we're going to write this because we have an OR here. This is alpha D. It goes through, it follows path alpha and then gets detected, or it follows path beta and then it gets detected, and we use the sum rule for this, and this is going to be equal to the probability of alpha D given, oh, wait a minute, this is, I've already forgotten what I was asserting, that the particle, we have to keep track of all our conditionals. I'm sorry about that. So this is alpha D or beta D, and then given that it started at the source and both slits are open. So here we go. We have an OR, and this is going to be processed using the sum rule. So we have alpha d SAB plus P beta and D SAB minus the probability of alpha beta D, the and SAB. Very good. So now we can simplify this a little bit. We said here that the particle has definite positions at all times. So if it has definite positions at all times, a statement like this one, the probability of following path alpha and path beta is necessarily not possible. So this guy here is equal to 0 because the particles have definite positions at all times. It cannot be up here and down there. So our model indicates already that. And so what we have at this point is that P alpha or beta D SAB is just the first two terms. Alpha D SAB plus P beta D SAB. Very good. Next step in the argument. Let's clean this up a little bit. Now, on the left-hand side, we have a product. We have a conjunction and so we're going to use the product rule. So we're going to write this as SAB equals the probability of detection. Let's do it as the probability of D given SAB, which is what we were interested in the first place, multiplied by the probability of alpha or beta given SABD. So that's the product rule. Now, what can we say about this guy here? Remember, the idea here is that the particles cannot jump. So the particle cannot go from S to D unless it follows continuous trajectories. So what is the probability that the particle achieving D goes from S to D follows either the path alpha or the path beta? Well, the model implies particles having definite positions following definite continuous trajectories, that this probability is 1. So that means that we compare these two equations here, this one, and it means that the probability that we are interested in, namely the detection at D when the source is at S and the two slits are open, is equal to alpha D SAB plus P beta D SAB. This is what we get from applying the rules of probability theory to our problem. In order to compare these two quantum mechanics, what I'm going to do is go back here, and what we want to do is rewrite this equation in the new notation. There is nothing wrong with this equation here, just like there is nothing wrong with an equation like this. It's just mathematical symbols, right? There's definitely nothing wrong. But because the notation is a little bit limited, it might misguide us to interpret it wrong. What I said here was, look, this PAV that appears here is when B is closed. In other words, when B is not open. While this one here is the case when A is closed. So what we wrote here, if we translate it into the new notation, is that the probability of a detection at D when the particle originates at the source A and both slits are open is the probability that the particle goes through is the sum of the probability, sorry, it's the probability that the particle is not the probability that the particle, the probability of going in the path alpha and the particle is detected when A is open and B is closed, plus the probability that the particle follows alpha and is detected when S, the particle originates at S, A is closed and B is open. So this is what quantum mechanics says. This is what probability theory says. Clearly, the two are not in disagreement because they refer to different probabilities. This is the gist of the argument. There is no problem. Now, it's very important to figure out what it is we proved and what it is we have not proved. What we have proved is that the rules of probability theory here are not necessarily incompatible with the rules of quantum mechanics. How we actually derive the rules of quantum mechanics, that's another issue. We will tackle it later towards the end of the course. But at the very least, there is no incompatibility between quantum mechanics and probability theory. The other thing we can actually do is try to figure out how it is that people have been led to believe that there is a problem with quantum mechanics and probability theory. Where precisely was their mistake? How precisely were people led into this kind of language? Suppose that we look at this expression here. I'm going to write it out. Suppose we were the temptation is to substitute, what was it we had here, the one I underlined, P alpha D SAD. P alpha D. Let me go retrace my steps and write another formula here. Before I do that, let me rewrite this equation here of probability theory, because here we have a product, right? And here we have a, we have a conjunction and a conjunction. Let me make this a little bit more explicit. I'm going to say P of D is given SAB is going to be the probability of going through alpha SAB multiplied by the probability of D going through SAB through alpha. This is just the product rule plus another term for the probability of following path beta multiplied by detection given SAB following path beta. So here we just use the product rule. Use the product rule. And now I'm going to make substitutions that are wrong. The substitution that is wrong is to say the detection when you know that you're following path alpha and both slits are open is equal to the probability of detection when you know that you're going through alpha, but the slit B is closed. So what I'm saying here is the probability of detection, given that you know you're going through the slit A, you know that you're going through slit A, is independent of whether the slit B is open or not. Wow, how could it not be like that, right? If you know you're here, how can changing a slit, opening up a slit somewhere else, make any difference? And the other assumption that we are going to make, that's also wrong, is to say the probability of going through alpha when both slits are open is the same as the probability of going through A when B is closed. Now, what's really insidious about this substitutions, you could say that they are motivated by a classical intuition, is that if you were to have a bunch of particles maybe going under Brownian motion or something like that, and you were to make them go through slits, some particles will find the upper slit. And there is a certain probability, of course, that they find the upper slit and they get detected. And the probability of finding the upper slit is completely independent of what the bottom slit is doing. So what's really annoying about this kind of assumption is that sometimes they're right. We can write similarly for B. Similarly for B and beta. And when we do that, what we have is that the probability of B, given that when we make these substitutions, we get the probability of alpha given SAB closed, probability of D SAB closed, plus probability of beta SA closed D, probability of D SA closed B beta. And we can use the product rule to recombine these guys here into P alpha D SAB closed plus P beta D SA closed B, which is exactly what we had down there. So now you see why it is that it's easy if you have a classically trained or classically brainwashed brain to make these substitutions. And what is actually being said here, and this is, let me put this as being very clear, this is wrong. These substitutions are not, let me put it like this, these substitutions here are not something that can be derived from probability theory. These are additional assumptions that we make on the basis of a classical intuition. And these are the ones that are wrong. So Keeping track, to conclude, keeping track of what it is you're being conditional on is actually important sometimes. Sometimes we're going to be very lazy and we may skip it, but you always have to be very aware that by not having a fully developed notation, you may actually be making a big mistake. Very good. So what have we learned about quantum and classical probabilities here? Well, quantum probabilities are not really necessary. It is perfectly okay to just use standard probabilities and try to do quantum mechanics. Whether we succeed with such models or not is another story. But at this level, there is no contradiction. The other thing that we have actually learned is coming from something like this. You have a source and you have slits A and slits B, and you have your detectors. We know in these particular statements here, we compute the probability going through path alpha. We know in this particular case here that we're going through alpha. The question is whether we open or close the second slit makes a difference. And what our analysis says, quantum mechanics is telling you is that it does make a difference. So conclusion. Quantum mechanics is not in conflict with probability theory. Quantum mechanics is strange, not because it is in conflict with probability theory, but because it is non-local. The particle is over here. The particle is up there. That's the assumption in this probability assignment. Whether you open or you close the other slit, which is far away, next galaxy, makes a difference. So what's really weird about quantum mechanics is the non-locality. Anything else I want to say here? I think that this may be it for now. So, and of course, our assumption that just standard probabilities are of universal validity still holds. Okay, I'm going to change the subject slightly now, and for the next 10 minutes or so, I would like to discuss the issue of expected values. Of course, you know everything I'm going to say now. You already know it. I'm doing it for completeness. Expected value and the variance. Suppose you have a probability distribution. So here we have the probabilities, and you have a variable x, and you have a probability distribution like that. It's a function. It can even be messy. So how do you, remember, these are things we use for reasoning. So wouldn't it be interesting if instead of having a whole function to describe our state of uncertainty, we could sort of summarize what this probability distribution is saying by a single number or two numbers? Well, one reasonable number to choose is the average. So the expected value is going to be denoted like this, and by definition we're going to just do all the sum of all the values of x multiplied by the probabilities of x. Very good. Here I drew a continuous distribution. Here I'm being discrete. I'm sure you can figure out how to adapt the two situations. Now there are two things I would like to caution you about the use of expected values. And the first one is that expected values need not be what one expects. So the term expected value may be very misguided. For example, when you toss a die, the expected value of the outcome, the i's are 1, 2, 3, 4, 5, 6, the probabilities are 1/6. So the expected value of i's divided by or multiplied by the probability, which is 1/6. So here we're summing from 1 to 6, and when you do the calculation, 1 plus 2 plus 3 plus 5, all divided by 6, this is 21 divided by 6, which is, what is it? 21 is 7 divided by 2, it's 3.5. Now this expected value, the expected value when you toss a die, is actually sort of interesting, because if there is one number that you cannot expect to get, is 3.5. You're going to get 3 or you might get 4. You never get 3.5. So the term expected is misguided. Here's another one. Suppose that you have a probability distribution that is bimodal, something like that. You live half the time in Albany and the other half of the time in New York City. What is the expected value? The expected value of x lands somewhere in there. So the expected value of where do you live would be somewhere, I don't know, in the town of Kingston or something like that, halfway between New York City and Albany. And this is clearly not where you're expected to be found, right? So when you have nice distributions that are unimodal and things like that, then the expected value is a useful quantity. When you have bimodal distributions, here expected value is not useful. Okay, so that's a couple of remarks about expected values. It need not be what you expect. Here, now let's talk about, remember what we're trying to do. Okay, let me go back. What are we trying to do? We have a whole function here, and we want to describe it by few numbers. One of them is, where is the function located? Where does it concentrate? That's expected value. That's pretty clean. But we would also like to know a little bit more about it. And the other thing that we may want to know is, how wide is it? And how wide is it is some kind of measure of how much you deviate. How likely is it that you're going to get measurements or values that differ from the mean? So we would like to have, we want a measure of the uncertainty in the distribution and we mean by what we mean by that is some measure of the width of the distribution, how much you expect to deviate from the mean. Very good. Here, how do you do that? We have to, this is not a matter of truth or derivation. What this is a matter of designing a number, a quantity that will tell us whether we're dealing with a broad distribution or a narrow one. And so what we could start, so this is a tentative quantity, a tentative measure of the width of the distribution. We could say, suppose that we take the quantity x and we calculate the deviation from the average, from the expected value, from the mean, and then we just take the average of that. That's a possibility. So let us see what we get. When we compute the average of the first term, we just get the average. Now for the second term, what we have here is just a number. This is the number, like for example for the die, this is the number 3.5. What is the expected value of 3.5? Well, it's 3.5. The expected value of a constant is just itself. So conclusion, the quantity that we have just written down, which is like a first tentative attempt to figure out a measure of width, doesn't quite work because it's always identically zero. And you can now that we see that we get zero, we can see why that happens. And it's because when you're taking the average of the deviation from the average, this quantity here can either be positive, and just as likely it can be negative. So these numbers, when you take the averages, are going to cancel out. And that's exactly what happens. The deviations can be just as positive as negative. So having diagnosed the problem, we have a second attempt, which may be the following. Well, if it is actually true that the reason this one doesn't work is because these numbers here, the deviation from the mean, can just as often be positive as negative, how about if we just take the deviation from the mean and take the magnitude? And then we take the average. This is perfectly okay. This is a perfectly nice measure of the width of a distribution. However, and unfortunately, this is sort of like taking magnitudes is always a pain in the neck. And so while this is a perfectly measure of width, perfectly decent measure of width, it is inconvenient. It's not easy to compute with. So a third attempt is to take the deviation from the mean, make it positive by taking the squares, and then you average, and this quantity here, which is called, it's a square, right? So this quantity here is the variance. It's a measure of the width, and it has the great advantage that it's a measure of the width squared, okay? It has the great advantage that it is very convenient for computations. And if you want the actual width, take the square roots. This is called the root mean square deviation, or the standard deviation. There is a nice identity that just like here we have an interesting identity up here. There is a nice identity that you may want to prove for yourself, which is that the average of the square of the deviations from the mean is the same as the average of the square minus the square of the average. So this is a useful identity. Very good. Caution. when you have a distribution like this, it does make sense to measure the width in the way by using the variance. This is good. However, if you have a probability distribution that is by model, then this width that you get by just following those formulas is not quite useful, right? You can see obviously that this is what's going on here. You can define this quantity, but the variance for multimodal distributions, the variance can be computed, but it is not useful. So I hope you see that some of these quantities that we define are really defined because they end up being useful tools for interpretation of how probabilities work, but not necessarily because they're being derived in any particularly deep way. Just the mean tells you where the probabilities are concentrated. The variance tells you how broad the distribution is. There is another aspect of this that I would like to end this segment of the lecture by pointing it out to you. When we say that we have a probability distribution, oops, what's wrong here? That has a certain width. What is being said here is that we do not know what the value of x is. And there is a certain uncertainty about what x might be. This is a warning here. The fact that you are uncertain about the quantity x does not mean that x is fluctuating. Being uncertain about x, and you measure the uncertainty through the standard deviation or the variance or something like that. Being uncertain about x does not mean that x is undergoing any kind of fluctuation. It may be that x is undergoing fluctuations, and that is the reason why there is uncertainty. If you're following the price of something in the stock market, this quantity may be fluctuating in all sorts of ways. And that's why when you ask what is the value of x, there may be uncertainty. Yes, that's one possibility. But it needn't be. It may be just that you happen to be ignorant about what the value is, or that you computed the probabilities on the basis of a certain amount of information that does not help you to answer the question, what is the value of x, completely. It just gives you a ballpark, the average, the expected value, and it gives you some uncertainty. Now, why does this matter? Well, understanding probability matters. We just saw that when we saw the double slit experiment, how if you have a wrong idea how probabilities function, you may actually be led into completely wrong physics. Well, one of the things that happens in quantum field theory is that the pieces of information that you incorporate into the theory in order to make predictions about the values of fields is inadequate. Is insufficient. So there are certain calculations or certain estimations that you may do about fields that give you very precise answers. But there are some others for which the answers are completely uncertain. If you calculate what is the variance of the value of a field at a point by following the rules of quantum field theory, what you're going to find is that the fluctuations are infinitely large. Wrong choice of words. The variance is infinitely large. This is one of the awful infinities that appears in quantum field theory, right? Now, if you confuse being infinitely ignorant about a quantity with the quantity fluctuating infinitely, you're going to be led to all sorts of really awful problems, because if the fields can fluctuate tremendously at a point, associated to those fluctuations, there are going to be energies. And those energies are going to be divergent as well. And if you couple those to gravity, you're going to be in deep trouble. And you may be even led into thinking that space-time, because there are infinite energies involved, is going to be infinitely warped. And you might want to invent models of space-time in which your space is really very, very random. It's a space-time foam. But now you see what my previous remarks are actually very relevant. The fact that you are very uncertain about the value of a field does not necessarily mean that anything real is fluctuating, and so you might be led into trying to fix a problem that doesn't exist, or fix it in the wrong directions. So it matters a whole lot to realize things like this. When you are uncertain about the quantity, it does not mean that the quantity is actually fluctuating. Very good. Enough for now. I'll come back in a little while and continue this lecture. Thank you.